Hello. In today's topic, we're going to be studying the Pythagorean theorem. I know that you've seen it before, but we're going to be kind of looking at why it's true and applications of it as opposed to just mostly using it to complete mathematical questions. So as a lead-in, this first part is not in the notes, just follow along. Consider a triangle, a right triangle, meaning there's a 90-degree angle that has sides of 3, 4, and 5. What we're going to do is we're going to attach a square to each side whose side lengths are the length of the respective side of this triangle. So for example, the side that has length 3, I'm going to put a square on it that is 3 by 3. The side that is 4, I'm going to put a square on it that is 4 by 4. And the side that is 5, I'm going to put a square on it that is 5 by 5. What you might notice is there are 5 by 5, there are 25 pink squares. How many blue squares are there? Well, there are 9 here and 16 there. If I add 9 and 16, I get 25. So what do I notice? The total number of pink squares plus the total number of blue squares are equal to one another. So what is it? So 25 is equal to 25. And how did I get there? I got there from the pink one because this was 5 squared. I got there from the blue one because it was 9 plus 16. 9 came from 3 squared. Oops, let's go back. I wanted to write that as 5 squared. 9 came from 3 squared, and 16 came from 4 squared. So do I see, hey, this is the sum of the squares of the two smaller sides of the triangle. We call that the legs. That's equal to the square of the longest side, and that is known as the Pythagorean theorem. We'll write it down in a second. So that's kind of a beginning proof to it. I'm going to show you more of a visual proof, and then we'll do a more formal mathematical proof. Here is a water demonstration of it. So they begin, and you'll notice the area of water is going to be the total of the legs, and then as it turns, it goes to the longest side. I guess it's also a volume, depends on your perspective. Rotate it, and the water from the two legs fills the square of the longest side, and it's equal. And then it works also the other way around. The square of the longest side we call the hypotenuse will fill up and be the sum of the squares of the two smaller sides. So this is a relation between the sides of a triangle and the area of the squares attached to the lengths. But the nice part is because I can undo squares with square roots, as we've seen in this chapter, I can solve for missing side lengths of right triangles using the Pythagorean theorem. So we call this the Pythagorean theorem. The Pythagorean theorem relates what we call the hypotenuse to the leg. So before writing the formula, we should define what we mean by hypotenuse. The hypotenuse is the longest side of a right triangle. A right triangle meaning that one of the angles is 90 degrees. The Pythagorean theorem only works with right triangles, but right triangles are throughout our world. The legs are the two smallest sides. The two smallest sides of a right triangle, or essentially the two sides that are not the hypotenuse. The Pythagorean theorem then is the relationship between the legs and the hypotenuse, and we've seen the square of the two legs, in this case a and b, a squared plus b squared is equal to c squared. And it doesn't matter which one you call a and b. You could write this as b squared plus a squared equals c squared. The order of the two additions doesn't matter. We call this the Pythagorean theorem. It's called the Pythagorean theorem because there was a man named Pythagoras that lived in the ancient Greek world, which in this case was actually in Rome. Well, it spread throughout the Middle East. He was born, as it says, in around 570 BC, and he developed he didn't develop, but he was the head of a large academy. You can kind of think of it like a school of today, and people studied math and science and astronomy there, and that school was one of the first to publish this result, a squared plus b squared equals c squared, and so it was named after the head of the school, the Pythagorean, Pythagoras. So another little side history lesson I'm going to give about the Pythagorean theorem that some might find interesting. This is not in the notes. You can just kind of sit back and listen for a minute. This has to deal with a man named Euclid who lived about 200 years after Pythagoras in the same area of the Greek Empire. He lived actually in Alexandria, which is in Egypt. Very little known about Euclid's life pre-adulthood. By the time that he was 20, he had arrived at the library at Alexandria, and the library at Alexandria was like the predominant school throughout the world at that time. Although it was not generally accepted, many scholars claim there is a proof that he received his formal training at Plato's Academy in Athens in Greece. Here he would have been trained by Plato and Aristotle and other famous Greek thinkers. He is not famous really for creating any new groundbreaking mathematical discoveries on his own. However, he was the very first that thought to put all of these ideas into a book, and that book became what we call Euclid's Elements. It's the very first mathematical textbook of the world. It was actually the textbook that was used up until about 150 years ago. So if you had learned any math up to about 150 years ago, you would have studied it out of what is called Euclid's Elements. Famous people as Newton studied Euclid's Elements, Gauss, Abraham Lincoln all studied Euclid's Elements. The Elements is the most important mathematical textbook of all time. It was written about 2,300 years ago. Pieces of reprints have been found that date back to 225 BC and were discovered in Egypt. Copies of the original were made, and the oldest intact one currently resides in the Vatican, just outside of Rome, dating to 888 AD. The book itself is a geometry book, and it consists of a variety of different types of geometry. However, the very first book in that 13-book collection is a proof of the Pythagorean theorem. So that's kind of why I'm talking about it here. Here's a piece of a picture of the very oldest copy of Euclid's Elements. So the Greeks became very famous. They're kind of the original mathematicians because they were the first to publish mathematical ideas. However, they were not the first to actually kind of think about mathematical ideas. This was found about, I think like 150 years ago, about 150, 100 years ago. And it's on a clay tablet. It was found in Babylonia, so the Middle East. And we call it Plimpton 322. It was artifact 322, named after one of the man who found it. It was dated back, we used carbon dating, and dated back to about 1800 BC, which is, 1500 years before Euclid. And it contains the following columns of numbers. So if you look 119, 120, 169, 65, 72, 97, 4,961, 6,488, 161. And at first we thought these were just random numbers. But if you check with the very first one, like 119 squared plus 120 squared, don't know why my pen's freaking out, it actually is equal to 169 squared. So actually these are what we call Pythagorean triples. They're numbers that obey the Pythagorean theorem. So actually the Pythagorean theorem was known well long before actually Pythagoras. The Babylonians knew it 1500 years before, but the Greeks were the first to write it in a book. So that's just a little bit of history about the Pythagorean theorem. Now we're going to use it. So it's used to calculate sides of triangles as long as we have a right triangle. They're used for ramps. They're used in construction a lot. So here's an example. A building access ramp has a horizontal distance of 24 and a vertical distance of 2. Find the length of the ramp to the nearest tenth of a foot. So we're really finding the hypotenuse. This could be thought of as A, this is B, and I'm after C. So I know A squared plus B squared equals C squared. In this case, A could be 24. Which one you call A and B doesn't matter, but C has to be the longest side. The longest side is always directly across from the 90-degree angle. 24 squared plus 2 squared is equal to C squared. Then I type in the calculator 24 squared. I get 576 plus 4 is equal to C squared. That's going to make 580. And now how do I solve? I use what we used all chapter. I take a square root. And when I take a square root, normally I would write two answers, but in this case, we're talking only about positives. I get 24.08. It says round the nearest tenth, so I get 24.1 feet. So that is how long the ramp would need to be. So there's example 1, solving for the hypotenuse. Example 2, again, a construction example, because that's a lot of the time where it gets used. A contractor is designing a house that has an 18-foot roof on a 10-foot tall attic. What is the span of the house? The span is how wide the house is. So I need to find a right triangle, and the right triangle in this case is right here. So I pop this triangle off, and I see that the hypotenuse is 18. B, because I usually like to think of A as the flat side on the bottom, it kind of looks like that. So I know a squared plus b squared is 10 squared is equal to 18 squared. A squared plus 100 is equal to 18 squared, and 18 squared is 324. Subtract 100, I get a squared equals 224, and then I take a square root. And like I said, normally when you take a square root, you need to write plus minus, but in this case, we can't have negative lengths, so I only write the positive, and I get 14.97. However, that is just from here to there. The whole span is going to be 2 of those. So the whole span is going to be 2 times 14.97. 29.94. And I think that we are measuring, because this is a word problem, we need to include our units. We're measuring in feet. So you can denote feet either by using FT, or actually you can put a little apostrophe, and that implies feet. So A is 14.97. The whole span is twice of that, so 29.94. Gonna give you a chance to try. Oh, it looks like I've got one more. Sorry. So last example is kind of an interesting one. It gets asked a lot like an ACT or SAT questions. The question is, what is the length of the shortest path an insect could fly to get from point A to point B? If this was like a box, you can think about it as a room. It'd be a very small room because it's 1 foot by 1 foot, but you could think about it, it'd be the same scenario. So I want to know, what's the shortest path from A to B? So I need to get from A to B, straight line. And how I'm going to do it is I need to break this into actually 2 Pythagorean theorem questions. So I'm going to find this bottom distance from A to this corner down here. So I need to find this, because if I can find this blue distance, I actually have this red distance already because it's 1. If I have the blue and the red, I can then get the green. That's the total diagonal of the cube. Down below, I can get the blue because this blue one looks like this. This is 1, this is 1, and this is the blue distance. So I could find that by doing 1 squared plus 1 squared equals c squared. 1 squared plus 1 squared is 2 equals c squared. Take the square root of both sides, and then I get, oh, that's the square root of 2. So from here to here is the square root of 2. Now I can use the blue and the red to then find the green. And the result is kind of an interesting property of mathematics. So the picture looks like this. Blue, and I've got my red, and I've got my green diagonal. My blue is the square root of 2, my red is 1, and my diagonal is my green c. So then I know 1 squared plus the square root of 2 squared is equal to c squared. 1 squared is 1, the square root of 2 squared, the square root and the square undo each other, so I just get 2 equals c squared. 1 plus 2 is 3, and then I get the square root, and my final answer is the diagonal is just going to be the square root of 3. So the distance from one diagonal to the other diagonal for a cube, if it's 1 by 1, is the square root of 3, which is interesting because if it was in 2 dimensions, just the bottom, it's the square root of 2. So in 2 dimensions, the square root of 2. Once you go to 3 dimensions for the cube, it's going to be the square root of 3. And you could extend this to like a 4th dimension. If you could see it, it'd be the square root of 4. 5th dimension, square root of 5. So it's kind of an interesting property of the Pythagorean theorem in different dimensions. Going to give you a chance to try kind of a basic question though, and here's yours. This again comes from a construction situation. So how long should the stringer be if we're going to construct the following staircase? The stringer is the side of the stairs that supports the steps like on a patio or a deck. So the picture looks like this. We really want to know how far is it from there to there, and here's our right triangle. This is 9 foot 9 inches. This is 8 foot 6 inches. You'll notice the very first thing you need to do is you need to convert both of these to either be in feet or inches. You can't have a combination. So that's step 1. Convert them to either feet or inches, and then work the problem. I'm going to pause the video now, or ask you to pause it, give it a try, and come back once you think you have an answer and you want to check it. Okay, I'm going to work it in feet. This is 9.5 feet. This is then 8.5, or this is not 9.5. 9 inches is 3/4, 9.75. And 8.8 feet, 6 inches is 8.5 feet. Then I'm going to do the Pythagorean theorem on it. So I've got 9.75 squared plus 8.5 squared equals c squared. 9.75 squared plus 8.5 squared gives me 167.3125. take the square root of that, and I'll have my answer. It'll just be measured in feet. So I get 12.93 equals C. That's in feet. If I want to get it to inches, I multiply that number simply by 12. So if you did it in inches, it'd be about 155.2 inches. And to denote inches, we use two apostrophes. So there's the two answers you could have got. You only needed to do either feet or inches. You didn't need to do both. Last part is the fact that actually the Pythagorean theorem is true both forward and backward. So the theorem says this: if a triangle is a right triangle, then we know a squared plus b squared equals c squared. But actually it's true the other way around. That means if I say this piece first, if a squared plus b squared equals c squared, then I actually know the triangle is right. So actually the Pythagorean theorem allows me to check whether a triangle is a right triangle or not. And we would call that a Pythagorean triple. So for example, could there be a right triangle that has sides 8, 9, and 12? Well, I just need to see, does it make the Pythagorean theorem true? If it does, then that could be a right triangle. If it's false, then it's not going to be a right triangle. 8 squared, 64 plus 81. We're looking to see, is that going to be 144? Well, when I add 64 and 81, I get 145. So no, these side lengths are not going to make a right triangle. What about 7, 24, and 25? 7 squared plus 24 squared. The question is, does that equal 25 squared? Well, 7 squared plus 24 squared is 625, and 25 squared is 625. So yes, it is possible to have a right triangle that has 7, 24, and 25 as its side lengths. So I can check it by using the Pythagorean theorem. If it's possible, we call that a Pythagorean triple, and that's what the Babylonians were looking at on their clay tablet. They were essentially listing all the Pythagorean triples that they could find. I'm going to ask you to try one, and then that'll be it. So use the converse of the Pythagorean theorem. The converse is when you say the statement in the reverse order. Use the converse. Check whether a squared plus b squared equals c squared to see, could there be a triangle that is right with the following dimensions. Pause the video now, come back after you've had a chance to try. Okay, you should see for the first one, it is true. 12 squared plus 9 squared does equal 15 squared. So that is what we would call a Pythagorean triple. You can make a Pythagorean theorem with it. The second one is false. That is not going to make a Pythagorean theorem true, so it is not going to be the sides of a right triangle. It will not be a Pythagorean triple. And that is it for today. The rest of the time is for you to work on the homework. Thank you very much, and have a good day.